In this video, I will show you how to solve vector word problems. The first one will be simple, and the second one will be a little bit more complicated. Justin leaves school and walks 17 kilometers due north. Justin then walks 10 kilometers due west. What is Justin's direction and distance from school? So normally when I'm doing a vector word problem, I set up a table like this one. Okay, and in each column I record information about a vector. So Justin leaves school and he walks this distance, and then he walks the second distance. Okay, so I'm just going to call the first vector distance 1, and I'm going to call the second vector distance 2. All right, normally I find the magnitude and the direction of each vector. But this problem is simple because we're only dealing with north and west. There are no directions that are going at an angle, or northeast or southwest or anything like that. It's just directly north and directly west. So we won't need to deal with the magnitude and direction. Instead, we can focus our attention on component form, okay, which will be like this. Okay, we'll go straight to component form. So the first distance is 17 kilometers due north. Okay, so that's 17 kilometers north, like that. We can write the component form for that. There is no horizontal component, all right, so I'm just going to put 0. And the vertical component is positive 17 because north. How about distance 2? He walks 10 kilometers due west. So that's like this. Boom. 10 kilometers. Should put units on here. 10 kilometers due west. We can go straight to the component form for that. The horizontal component is going to be negative 10 because it's west. All right, the entire magnitude is going to the west. If it were to the east, it would be a positive 10. The vertical component is going to be 0 because there is no vertical component. It's all horizontal. So that's it. We have distance 1 and distance 2. Now we can find the component form of the resultant vector by simply adding these together, the corresponding parts. So that would be negative 10, comma, 17. All right, 0 and negative 10, 17 is 0. Boom. Now, oh yeah, I forgot to label this. This is the column where we do the resultant vector. Okay, now we will need the magnitude and direction of the resultant vector. Because this is negative 10, 17, that's left and up, or west and north. So we know we are going to be in the second quadrant. Okay, let's make a triangle out of that. Actually, let's start with the magnitude. All right, I should go kind of in order. So we need the magnitude and the direction. So we can find the magnitude using the magnitude formula. So we will simply do negative 10 squared plus 17 squared. Just go ahead and put that in your calculator. I'm getting 19.72. So that means 19.72 kilometers. All right, that's the total distance from school that he walked. That's the total of these two distances if he walked directly. Now we need the direction. So I feel like changing colors for a second. For the direction, we're going to need this reference angle right here, and let's go ahead and make a triangle out of this. Little right triangle. Okay, it was left 10 and up 17. So this is basically negative 10 and 17. So we can find the reference angle using the tangent function. Tangent of r, that's opposite over adjacent, so this is going to be 17 over 10. I'm ignoring the negative sign because I just want the positive value of this angle. The reference angle will equal the inverse tangent of 17 over 10. So the reference angle is 59.53 degrees. However, the direction is going to be measured from the positive x-axis like this. Let's call it theta. Theta was on its way to being 180 degrees, but it had to stop short by a measure of r. So theta should equal 180 minus r, or 180 minus 59.53. So the direction is 120.47 degrees. Now, we like to give the direction in the same way that the direction was given in the original problem. And they didn't give us direction as measured from the positive x-axis. They said due north. They didn't say 45 degrees, for example. They said due west. They didn't say 180 degrees. So really, we should use a different system for the direction, involving north, south, east, and west. So, for example, what we could do is, let's see, look at that reference angle. We could think of this vector as being, if we think of it as starting to the west, let's see, what's the best way to do this? All right, we can think of it as starting to the west and then turning r degrees towards the north. Okay, so this direction could be thought of as west, and then we turn 59.53 degrees towards the north. So this is a more appropriate way of writing the direction for this problem. What was that? 59.53 degrees north. And that's it for this problem. All right, let's do one more example. This one is a little bit more involved because it involves directions that are not simply north, south, east, or west. A plane traveling 385 miles per hour is flying at a direction of north 42 degrees east. There are force winds of 53 miles per hour from a direction of south 70 degrees west. If no correction is made for wind, what is the resultant speed and direction of the plane? Round your answer to the nearest tenth. Show all work. Well, speaking of showing all work, kabam! I like to show my work on an organizational chart like this one. So let's see. We have the plane and the wind. So those are the two vectors we will be dealing with. So I will record those vectors in these columns. In the third column, I will record the information about the resultant vector. In the first row, I will record the magnitude r and the direction theta of each vector. In the second row, I will record the component form x comma y for each vector. So let's start with magnitude and direction. For the plane that is traveling 385 miles per hour, that is the magnitude, 385 miles per hour. The direction is north 42 degrees east. Let me write this down. North 42 degrees east. Now, this is not the direction that we can use for the chart. All right? For the chart, we have to find the angle of the vector measured from the positive x-axis. So what does this mean? North 42 degrees east. That means imagine starting at north and turning 42 degrees towards the east, like this. So that would give us a vector like this one, where again the angle that we turned was 42 degrees. Okay, so this is the position of the vector at direction north 42 degrees east. Now, the direction angle that we need for the chart has to be measured counterclockwise from the positive x-axis. So we need this angle theta. Well, clearly this angle is going to be 90 minus 42, all right? Because together these two angles make 90 degrees. So theta is 48 degrees. And that is the direction that we need for the chart. All right, so there is our magnitude and direction, r and theta. Let's do the same thing for the wind. What do they tell us about the wind? The wind is 53 miles per hour, so guess what? That is the magnitude, 53 miles per hour. Now what about the direction? From a direction of south 76 degrees west. Okay, so south 76 degrees west. That means start at south and turn 76 degrees towards the west. That will put us in the third quadrant. So let's draw a vector that is in the third quadrant. Okay, we turned 76 degrees towards the west, so that means this angle right here is 76 degrees. But the angle theta that represents the direction has to be measured from the positive x-axis. This is the type of direction that we have to use for the chart. So how big is this? Well, this angle theta was on its way to being 270 degrees. All right, it went 90, 180. If it went all the way around to south, that would have been 270. So I'm hoping you can see that theta is 270 degrees minus, because it didn't quite make it. So it did not quite make it the last 76 degrees. So it's 270 degrees minus the 76 degrees of the blue angle. So that means theta is going to be 194 degrees. And that is the direction that we need for the chart. So 194 degrees. All right, so that's the magnitude and direction of the wind. So unfortunately, there's no way to combine the magnitude and direction of each of these to get the magnitude and direction of the net result, the resultant vector. So we're going to have to find the resultant vector indirectly by converting these into component form. So if you know the magnitude and direction of a vector, you can convert to component form using the following little formula. Okay, it's going to be r cosine theta, comma, r sine theta. Alright, that's how you convert from magnitude and direction to component form. So for the plane, that's going to be 385 cosine 48 and 385 sine 48. Okay, that's r cosine theta, r sine theta. Alright, this is r, this is theta. So just put this in your calculator. So component form for the plane velocity is 257.62, comma 286.11. Now let's do the same thing for the wind. Remember, r cosine theta, r sine theta. Alright, this is r and this is theta. So for the wind, that's going to be 53 cosine 194 and 53 sine 194. Calculator. So the wind velocity in component form is negative 51.43, comma, negative 12.82. So what we need is the component form of the resultant vector, all right, the combination of the plane velocity and the wind velocity. And the way you can find that is easy in component form. Just add the corresponding components. So I'm going to add these horizontal components together, and I will add the vertical components together. And let's see what we get. So the resultant vector in component form is 206.19, comma 273.29. So for the final answer, we need to find the magnitude and direction of the resultant vector. So I need to convert component form back into r and theta, magnitude and direction. Let's start with magnitude. To find the magnitude, we can use the magnitude formula, where we take the square root of 206.19 squared plus 273.29 squared. If these are ever negative, you have to put the number in parentheses before you square it. So anyway, put this in your calculator and that will be the magnitude. I got 342.34 something. So that is the resultant velocity, the combination of the plane and the wind together. So 342.3 miles per hour. Now we need to find the direction. So let's see, direction. Here's how we find the direction. See how both of these components are positive? That means we are going to the right and up, or east and north, which means that we're talking about a vector in the first quadrant, which makes this a little bit easy. So it was right 206.19, or east, and I'm making a triangle out of this, by the way. And it is up 273.29. So for the direction, we're definitely going to need this reference angle right here. We're going to need this reference angle. And the way we can find that is by using tangent. Tangent of the reference angle is going to equal opposite over adjacent. So 273.29 over 206.19. Then the angle R is going to equal the inverse tangent of all of this, 273.29 over 206.19. Put that in your calculator. So the reference angle is 52.97 degrees. Now, before we do anything else, we have to remember, how did they give us the direction in the original problem? Because there are three methods we've learned about direction. We've learned to measure direction as an angle counterclockwise from the positive x-axis. Is that what they want? There's something called bearing, where you measure clockwise from the positive y-axis. Do they want bearing? Or there's another method where they have things like north, 42 degrees east, or south, 76 degrees west. Well, in this problem, they're using this method. So in our final answer, we need to write something like this, like south something west, or north something east, something like that. So we might as well use the reference angle. So we could think of this, the position of this vector, as starting from east and then turning r degrees towards the north. Alright, we can think of it as starting at east and turning towards the north by 52.97 degrees. Okay, so that would be east 52.97 degrees north. Starting at east, turning 52.97 degrees towards the north. Okay, so that will be the direction. So I'll just go ahead and record that in the resultant box for our final answer. Okay, now they said they wanted the nearest tenth, so I really should round this up. So I guess I'll go ahead and write 53.0 degrees north. Alright, because you got to round up. Alright, so that is the magnitude and direction of the resultant vector. So this is the final answer right here in this box. Ta-da! Alright guys, that's going to do it for this video. Go ahead and click here in the red apple to watch the next video. Click in the green apple to subscribe, or click the yellow apple for the full playlist.